Hey, it's Mr. K doing a video for AP Physics C Mechanics, continuing on from the intro video that was last time. We talked about some motion. This time we're going to talk about motion some more. We're going to talk about deriving, more of an official lecture on deriving. Not finding the derivative, but actually deriving. And let's just start off with where we were last time. We got a little bit of graph paper here. This is the same paper that we had last time, just flipped around so we have some grid on it as well. And let's talk about what we talked about last time. We talked about acceleration. So remember that acceleration, A, is a change in velocity over a change in time. That is something to consider. That's actually a great place to start. This is where we're going to start with for calculus as well, I think. But for now, algebra base. So what can we do with this? This is a ratio. Acceleration is just the ratio of a change in velocity over a change in time. And we can just move it around. So if we move it around, if I have an acceleration and I multiply that by a change in time, I get a change in velocity. Okay, simple stuff. But it's going to be very important. In this case, we're going to keep acceleration as a constant. Can acceleration be can it change? And sure, it can change. If you jumped out of an airplane, your initial acceleration would be g, your 9.8 or 10 meters per second every second. But it will quickly go down to zero as you hit terminal velocity. So that's a case of acceleration changing. When you hit the gas in your car, when you first hit that gas, if you floor it, you might accelerate at a very high rate in the very beginning, but as your car gets faster and faster, that rate of acceleration would probably drop until you couldn't accelerate anymore, because you're pushing through the air, the wind that your car is going through. So here we are, acceleration times time. That is a change in velocity. To make it even better, this acceleration times time, this change in velocity rather, is how do you find change? That's a final minus an initial, right? So this is your first kinematic equation. You know, it's besides this one, this is just the first kinematic equation. All this says, let's move this initial velocity over, is that if we have an initial velocity, if we add to it an acceleration for a period of time, we get a final velocity. Fantastic. All right. So easy first derivation for kinematics, the description of motion, how things move, or just what's going on. So if something is not accelerating, then that's a zero, and we can say the initial velocity is equal to the final velocity. Easy stuff. Let's also talk about velocity, because velocity is an average velocity. Let's say that. Let's be a little bit more specific. An average velocity is a change of position over a change in time. Okay, so average velocity, a change of position over a change in time. Well, we can do the same thing to that and just say, all right, average velocity times a time would give us a change in position. Okay, fantastic. If you know how fast you're going, if you are always going that rate, if you multiply by a time associated with that speed, I guess, that velocity, you would get how far you go. If I am moving at 50 miles per hour, let's say, if I'm moving at 50 miles per hour, if I multiply that by 2 hours, then I get 100 miles. Okay? Make sure the time is the same unit in that time that we're multiplying by and the time of the velocity itself. So, you know, that's pretty simple. Well, let's keep on going. What Yeah, that was a snoring dog back there. What would happen if we graph this out? And so let's go ahead and look at that same problem that we looked at last time, the ball dropping. So you have a ball, a rock, it's dropping down, it drops down a certain distance in a certain time, whatever it is. So let's graph this out. And we're going to start off pretty simply with the graph. And we're going to graph out acceleration. So if we were to graph out acceleration of this ball, we're going to graph it out by time. What is the acceleration of this ball? And as we talked about last time, the acceleration of the ball is, and always will be, in our flat Earth, infinite plane world that we have at the moment, no air, it's 10 meters per second every second. So whatever you draw, it's going to be a flat line, boring, unchanging, no slope to it, constant value of 10 meters per second every second, or meters per second squared. Now, what does that tell us about velocity? So, and again, I know that some would argue, hey, you're talking about negative, shouldn't it be on the bottom? Well, I mean, if we're always going the same direction, then that's fine. So, there we are. Let's talk about velocity. What would the velocity graph look like should we have a falling object under the influence of gravity for a time t? And so, as we talked about last time, here we are, we're falling, and we fall for 1 second. What's our velocity? And by definition, it should be 10 meters per second downwards. If we fell for another second, 2 seconds later, what's our velocity? After 2 seconds of falling, it's going to be 20 meters per second downwards. For another second, 30 meters per second downwards. And so every single second that passes, the velocity is going to increase by 10 meters per second that way. And so for the velocity, our velocity started off at rest, nothing. And every single second that passed, we got the same amount bigger every single second that passes. And so what that would result in would be a constant slope, increasing slope, actually no, not increasing slope, increasing value for velocity every single second. Okay? Now, what would that do to a position graph? And so if we drew another graph of position versus time, what would that do to our position and time there? I should just call it y. So if we started from rest, we started at, let's say, initial position of 0. After a certain amount of time, we would fall a certain distance. And let's just say we fell that distance. The question is, how did we get there? And so, I covered this last time, so if you just watched the other video, that's great. But if you fell for 4 seconds, 10 seconds, however many seconds you fall, what would the graph look like as time went on? Okay, and so, this is where I want you to think about it. If you need to, you should pause the video and actually think about it. What would the graph look like as time went on? If you are accelerating every single second that passes, every single half second that passes, every single time increment that passes, you are moving faster in this case. Acceleration could slow you down as well, but your velocity has changed. So if we go for the first second, you fall. And for the first second, you fall, let's see, 5 meters. Is that accurate? So let's kind of write it up. If you fall for 1 second, your initial velocity is nothing. Your final velocity, we've fallen for 1 second, It's 10. Your average velocity is 5 meters per second. So if you fall and your average velocity is 5 meters per second, you fall for 1 second, your change of position is 5 meters downwards. If you fall for 2 seconds, 2 seconds later, falling for 2 seconds, how fast do you get? It's 10 meters per second, 10 meters per second. That's 20 meters per second. Final velocity, if you started from rest. What's your average velocity? 10 meters per second, average velocity. How long did you fall for? 2 seconds. How far did you get? 20 meters. So we've gone falling 5 meters in the first second to falling 20 meters if we fall for 2 seconds. 15 more meters in that second. If we fall for 3 seconds, it's kind of beating a dead horse, but if we fall for 3 seconds of time, starting from rest, our final velocity is 30 meters per second. What's our average velocity? It's 15 meters per second, falling from rest. How long did we fall for? It's 3 seconds. 45 meters is how far we go. So we are falling faster and faster, and we are going farther and farther every single second that passes. This line for this position graph will be exponential. All right? It's going to be curved. The more and more and more you allow this ball to fall, excluding air resistance, the farther and farther and farther it's going to fall every single second that passes, starting from rest. If we instead did this, tossed it up, came back down, what would the graphs look like? Okay, so that's going to be a big question. I want you to think about that. Can you figure out what the graphs look like if instead of just dropping it, what if we threw it up with a certain velocity, let it fall back down, and we caught it again? Okay, let's stop with that.